Good morning, everybody. I would like to welcome you again on the second day of our workshop. And I will be giving the first lecture about the determination of molecular structure of polymers. As I said yesterday, no polymers are actually almost no polymers the same. And sometimes the differences we can observe in properties depend also on the small differences in structure. And I will talk mostly about this today. So first, some introduction why it is important, then I will say a few words about infrared spectroscopy, nuclear magnetic resonance, and size exclusion chromatography. These are three, I think, most important techniques, which are sometimes also used in a combination. So we can, because by using, for example, size exclusion chromatography or chromatography generally, some other as well, for example, nuclear magnetic resonance, we can really get deep insight into the polymer structure. So properties of polymers depend on chemical composition. So it's different. We have PVC, PMMA, PP. That's of course normal, but the properties depends also on their heterogeneity. And we have various types of heterogeneity. So one is molecular architecture. We have linear polymers, we have branched polymers with short branches, with long branches, and star-shaped polymers, as well as some other more exotic architectures. Then we have a distribution of molecular weights, which is very important, especially for processing of polymers, because some processing techniques, they require a broad molecular weight distribution, some require more unified. Then we have a distribution of chemical composition, as in copolymers, for example. Here we see three types of copolymers, which of course all has different, very different molecular, different properties. And of course, sometimes it's important also the distribution of functional groups, because functional groups are usually used for maybe for a further reaction, or maybe just for a modification of polymers. So this average chemical composition is usually determined by NMR or FTIR. The molecular weight distribution is determined by size exclusion chromatography. This is, I can say, standard, but of course we have other types of chromatographies as well. And the best thing, as I already said, is to separate polymers according to molecular weight or some other interactions, and then we check their structure by FTIR or NMR. So first I will say something about infrared spectroscopy. So infrared light has lower energy and therefore longer wavelength than visible light. And the measuring range, which is usually used in FTIR equipment, is 4,000 to 600 centimeters to -1. So it's a wavelength of 2.5 to 20 micrometers, depending on the instrument. And when the material, which polymer or something else, absorb this photon of this light, it gets excited and the oscillation of atoms starts. So we have various this oscillation. So we have stretching, which might be symmetrical or asymmetrical, then in-plane bending or rocking, and also out of plane, so out of like this. And so all those oscillation we can see as a spectra. So here, for example, we see one of the most simple polymer spectra of polymer polyethylene. And here at 2900 approximately, we see CH bond stretching. Here it's CH bending. And here is very little peak, several peaks, small peaks. And if we see peak at bend, not peak bend, at 1378, it means that we have LDPE, low density polyethylene. If it's at 1368, then it's high density polyethylene. So very small differences can tell us quite big differences about the polymer structure. So every bond absorbs photon at different wavelengths. And of course, they are also affected by nearby atoms. So not every CO bond absorbs at the same frequency. So we have, for example, C bonds in quite large this range, because it's nearby bonds also affect this position. And we can say that there are two parts of infrared spectra. One is this group frequency region from 4000 to 1300. And here, if we see some band that's usually very broad band at 3000 to 3600, we know it's OH or NH group. CH of alkanes is here at 2850 to 2970. If there are alkanes, it's slightly above 3000, and alkenes, so triple bond, there is a band at around 3300. Triple bonds can also be seen at 2200 approximately. Not only CC triple bond, also CN triple bond can be found somewhere in this region. CO, this is usually very strong band. It's between 1600 and 1800, and alkanes are around 1700 to 600 to 700. If it's aromatic ring, 1500 to 1600. Besides this, we have another region which is called fingerprint region. Here, the influence of whole molecule is actually observed in this region. So we can say that no two molecules give exactly the same infrared spectrum except enantiomers. So this one way, it seems like easy, something very easy, so we can make a spectra, and if we made it once, we know the structure, we know what it is. Actually, is also not that simple, because sometimes it's very important how we prepare a sample. STIR enables qualitative and quantitative identification, and we can analyze gases, liquids, and solids. However, as I said just before, it takes very experienced operator to do some quantitative work. For example, some years ago, we tried to determine the hydrogen bond formation in some polymers, and we just didn't succeed. But then we asked a colleague on another lab who is really specialist. He's doing just FTIR analysis. So, and he did it very soon, and very soon he published an article on the topic. We were just not able. Although we had equipment, we had everything, we were not skilled enough to prepare samples and also to operate with spectra. There are many things we can do with the spectra, not only that we obtain a spectra, and that's it. Then it's also what you do with it. It's also quite important. There are two techniques mostly used for making FTIR spectra. One is potassium bromide disc. So we take 1 milligram, approximately 1 milligram of the sample. We ground it with mix with 100 milligram of potassium bromide, and then we press it in a disc. And I must say this is sometimes quite problematic to obtain really good disc or to obtain reproducibility of results. And the second very much used technique now, actually here at the FTPO, we mostly use it, is ATR, attenuated total reflectance, which is shown here. This technique is actually much easier and much faster, I can say. Applications of spectroscopy in field of polymers, we can determine the type of polymers. Actually, there are some equipments for fast determination of polymers. So it's a kind of apparatus like a gun. You keep it in your hand and you just point it to the material and you get an answer whether it is polystyrene, polyethylene, or those most common polymers. Of course, with those laboratory instruments, we can find also other types of polymers which cannot be found by this kind of simple equipment. Then we can make a determination of the composition of some complex samples, composites, copolymers, blends. Here, usually we can, for example, we make a spectra. We see some signal of which do not belong to polymer. Then we make also some extraction of some other, we compare it and make extraction of other spectra, so we can also see, find composition, for example, of filler inside this. Then we can determine the tecticity of polymers, and also crystallinity can be determined. However, here we need some samples, usually compare with DSP to really find the right, to determine the intensity of the peaks and correlate it to the crystallinity. We can determine also the degree of cross-linking. Then we investigate the formation of breaking and formation of hydrogen bonds, what I explained before. And sometimes we can use it also for monitoring the course of reactions and polymerization or cross-linking we can do in FTIR. So here again is polyethylene copolymer propylene. We measure the sample, and the beauty of FTIR is that there are databases of various, not only polymers, but also some other chemicals, and we can soon make a comparison. So black one is our sample, and the red spectra is spectra of, from the database. And so here we can easily see whether this corresponds or there are some differences, and what differences could be. So this is a very easy and nice way to find some what we have. Here is one sample of butyl rubber. Actually, two butyl rubbers. One was the black one was good, the red one was not. And so if we look at those spectra, we hardly see any difference, except here in this region of CH groups at approximately 2,900 to 3,000. Here we see a small difference, and here that's how we found out that good butyl rubber contains more isoprene than a bad one. And more. Can you please turn off the microphone? Okay, now we can continue. But of course, those small differences in the DSC were not enough, so we confirmed also by DSC and by dissolution in solvents, because the less isoprene also meant that this rubber could not have been cross-linked properly, and so it was soluble in more or less soluble in solvent, while the good one wasn't. So sometimes it takes more than just one. Usually FTIR, I must be honest, it's not my favorite technique. I don't really like it much, but sometimes you can get very good results. But it's good always to combine several techniques of characterization. So here we see the determination of crystallinity of poly 3-hydroxybutyrate and copolymer with 4-hydroxybutyrate. These are biopolyesters, and they assigned a signal of crystals to 1227 centimeters, and the band at 1180 was assigned to amorphous phase. So here on the left we see the spectra of aged copolymer, which is pink, and remelted, which is green, and the fresh one is black. And we see that there are differences in intensities, and then they found out the very good correlation of this crystallinity index based on those intensities of those peak with DSC signal. So there is a quite nice correlation, and why is so we don't get directly crystallinity except if we compare it to the results of DSC. But once we have, why is this important? This polymer, this method could be used for determining the degree of crystallization in water suspension, for example, because in this region there was no influence of water. And using FTIR, we could determine the degree of crystallinity of any sample also in the, if it's suspension in water. Cis and trans configuration. This is A is one for cis only, mostly cis, and this is low cis polybutadiene. So it's quite a big difference between infrared spectra, and we can see what it is. And also tacticity, I said, here is the spectra of isotactic polypropylene on the top and atactic polypropylene on the bottom. We see it's a very big difference, and so also from this we can calculate some degree of tacticity. So that would be all about FTIR. And now we go to another spectroscopical method, so NMR. This is, I can say, my favorite. Actually, the basic of this NMR is similar to spectroscopy. So we have some absorption. Here it's radio frequency of different wavelength, and we get a signal. NMR can also be used not only for chemical characterization, but also for imaging, for example, in medicine. But I also know some people, they determined, for example, they made images of water penetration into the wood. So many things can be done by NMR one way or another. So what we have here on this picture And for measuring NMR, we have to have a magnet, a strong magnet. And then we have these coils for radio wave input and radio wave output. So the signal we get, and then the signal go to detector amplifier, and at the end we obtain NMR spectrum. So these are two types of NMR spectrum. This one is 500 megahertz. This is on the left side. It's over 2 meters large, big. And on the right, there is tabletop NMR. Usually those tabletop NMRs are much smaller. They don't need any liquid nitrogen or something to cool down. However, they work at 80, 90, 60 to 90 megahertz, which is better, more suitable for less complicated, for example, organic molecules, but also they can be used for polymers, but it's better to use a big one for polymers, to be honest. However, for routine work, I think this tabletop is also very, very useful for polymers. So how it works? We need nucleus with spin for measurement. So the atoms which has even number of protons and neutrons do not give NMR signal, which is pity, because most of the work, most of the organic molecules, they all based, not most, but they all based on carbon, and we cannot measure carbon-12. Then we can measure those atoms which had odd number of these spins, protons and neutrons, or they have spin 1.5 and so. So we can measure proton, C13, N15, and so on. And it's a good luck that every atom, like for example carbon, has at least one this is isotope which can be measured. So the reason we can make NMR of carbon is there is 1.1% of carbon-13 in nature, and this enables us most of the NMR measurements in organic chemistry. So how it works? Nuclei with spin, they rotate and they make small magnetic field. In nature, these fields are not oriented, so they're oriented randomly, so nothing. Once we put the sample in a strong magnetic field, this results in a partial polarization, and some spins are oriented parallel to this magnetic field, and some are oriented against the magnetic field. So these which are oriented parallel, they have somewhat smaller energy. And this difference in the energy of two levels depends on the properties of the nuclei, so gyromagnetic ratio, and the strength of the external magnetic field. So we use different magnets. We will have this energy at various frequency. So, as I said, we get net magnetization. Once we put a sample into the magnetic field, we get small net magnetization. So this is the difference between those two states. And then we apply another field at various frequencies, as I said, from 60 to 1200 megahertz now. These are the strongest as I know. And depending on this, the length and amplitude of the pulse, we shift this net magnetization into the XY plane. So, and then we stop this radio frequency, and the atom goes back into the normal position. So it relaxes. And we get this kind of signal, and by using Fourier transformation, we obtain a signal at a specific frequency. And of course, we do that once we don't get anything because the spectra is full of noise. So we have to collect many spectra to obtain a good signal to noise ratio. I said many, but that depends also on the nuclei that we measure. For example, if we measure proton, then it's just maybe 20, it's enough to make spectra. If we measure carbon, then we sometimes need thousands to get a good spectra. So now I said here, we get frequency, but what I said before, frequency depends on the magnet we use. So every NMR works at slightly different or strongly different magnet. So we would get results at different frequency, which is not very good. So we what we do, we use this with standards, and absorption is written as chemical shifts. So this in ppm depend on the frequency of the atom, frequency of reference, and frequency of the instrument. So every instrument gives us the position at the same place. For carbon or proton, usually we use this tetramethyl silan, which is shown here. But for other protons, we use other standards. And according to previously what I said about this mechanism, it seems that every proton should resonate at give signal at one at the same position. So, but that's actually not true. That would be not of much of the use. So the reason they show signals at various positions is that magnet also influences electrons around the proton, and so the nuclei is depending on the surrounding more or less shielded, and this shielding actually make the differences. And for example, this tetramethylsilan is very signals are very shifted, and so you can always find it on the right side of the spectrum. So this is how it is if we use different magnetic fields, for example, 11.75 Tesla and 2.34, we obtain signals at the same ppm. So how do we use this NMR characterization for polymers? Mostly what we use is proton and carbon-13 spectra. However, also nitrogen is sometimes used on then silicium as well, and phosphorus sometimes, other as well, depending on the structure, modification, whatever we do. We can use it for monomer and polymer identification. This is I think the easiest way to really see what is in polymer. From FTIR, for example, it's very hard to distinguish between polyamide 6 and polyamide 6,6 because the bands are more or less at the same position. But in NMR, it is a bit easier. Then we can estimate the average chemical composition of the sample. So it's if it's copolymer or homopolymer, and so we can determine end groups and so on. Then sometimes microstructure can be determined as well, configuration. Here we can have usually it's head to tail bonding of monomers, but sometimes we can observe head and tail as well. And this tacticity sequence distribution of repeat units in copolymers, or we can also determine the branching in polymer. N group is determination is important for determining average molar mass of the polymers. This is, however, can be done if molar masses or molecular weights are relatively small. If they are very high, then it will be very hard to obtain good NMR spectra to calculate this. Hydrogen bonds can be studied, dynamics of polymer chains can be studied, and also we can follow some reaction also within NMR. So we measure NMR one by one, and we see how the intensity of signal changes, and we can make also some kinetics of reaction if reaction is not too fast, I can say. And for polymers, we do this analysis in usually deuterated solvent or in solid state. So, for example, these dynamics of polymer chains can be done in solid state. I must say that solid state NMR also requires some specialist knowledge and also experience to obtain good solid state spectra. This is proton NMR. The measurements are fast, so in, let's say, 15 minutes, we can get a spectra and start measuring another one. Spectra are quantitative, so intensity of signal depends on the number of protons in molecules, which is very nice to determine the, for example, chemical composition of some copolymers. And so chemical shifts are in the range of 0 to 14 ppm, so the range is very, very small, which might be somehow sometimes problem. We can use very low concentration. However, with this is one way good if we work with polymers, because polymers usually increases viscosity of the solution, and then the resolution of spectra is not so good. So we can really put a small piece of polymer inside and get a nice spectra, well separated peaks. And we can also, from the shape of the signal, we determine the groups in the surrounding. However, with polymers, this is usually not the case. So here we can see that around about 10 we have acid, OH group of acid, aldehyde 9 to 10, esters, it's also somewhere here with at 9. Then benzene ring, this is around 7 to 8. Double bonds around 5 to 6, but here we have this many possible combination depending on the type of the atom which is nearby. What we usually can say, if it's somewhere between 0 and 1, that's most probably CH3 group, hardly to get something else. Carbon-13 spectra, the measurement takes hours. Sometimes we measured also over the weekend. So for 2 days or so to obtain good spectra. Spectra are not quantitative, but we can measure them also quantitative way. For example, some time ago I measured polymer with C double bond S group, and this was not observed, totally not observed under the normal measuring condition. So we had to change the measuring condition. So I finally saw some small peak, because the relaxation time of this CS group is so long that it's hard to see it. The number of signals corresponds to the number of different atoms, and or similar to previous to proton, we can, from the position, we can make some assumption what kind of polymers there are. And there are also some other techniques. There are plenty of techniques which can be used to determine also the type of C atom. So, for example, this is APT. Here we see a spectra with some signals on the top and some signals pointed to the bottom. And those on the top are signals of CH3 groups or CH. Down, there are CH2 and C, quaternary carbon are turned down. So this also helps us to get easier access to our structure. There are plenty of two-dimensional spectra. There are various techniques which sometimes they give also the same result, or at least for someone like me who just use this as a tool, the results are the same. So we have two-dimensional proton-proton spectra, and here we see the correlation with which proton is correlated to which proton, and also two-dimensional carbon and proton spectra. We see which proton corresponds to which carbon, and from the calculation of intensity in proton, we can also define whether it is CH2 or C or so on. There are also some 3D NMR spectra, but I must say, I don't know, I never came across to them, so I really don't know much about it. Probably there are more used for some proteins and bio stuff to analyze. So if we go to a practical example, carbon-13 of polyethylene. Here we see the different structures of polyethylene. We have several polyethylenes, and here there is assignation of those different carbons in spectra. For example, here it's better to see a high-density polyethylene, which is linear, and LDPA, low-density polyethylene, which is branched, strongly branched, with long and short branches. And we see here is actually a book of signals around 30, while here there are only some end groups. Polypropylene, mentioned yesterday. We have mostly isotactic polypropylene, also syndiotactic and atactic. And we see that there is a little difference between isotactic and syndiotactic polymer. Usually, since no one is 100% isotactic or syndiotactic, there are always some small signals also beside. And if we look at the spectra of atactic, we see just broad signals at relatively the same position, actually. So from this, we can see what kind of tacticity in our polymer is. So here is I wanted to show you how high electronegativity of fluor, polyvinylidene fluoride, shifts the signal towards higher chemical shifts. So here at 120, we see the signal of this carbon, and this actually is the region where we expect double bonds at 120 usually. But it's not double bond, it's because of high electronegativity of fluor. Now if I go to size exclusion chromatography, here we separate polymer according to their size, or better say hydrodynamic volume. Usually have stationary phase, which is a gel, porous gel, like shown here on the right side, and we inject. There is a mobile phase, so solvent is flowing all the time through this column, and then we inject a sample. And sample then since these beads are porous, the smaller molecule just enter the pores, and the bigger molecules cannot enter the pore, so they just float through. And here we see that the red molecules are big, and they just went through, and they elute first. Then somewhat smaller molecules elute second, and the smallest, for the smallest, it takes the longest time to elute us. So we can get this kind of spectra, the chromatogram actually. Usually this sec is not, we have to calibrate it with some polymers with very narrow molar mass distribution. Most commonly, we do that with polystyrene or PMMA. That means that the molar masses we get are not are relative, not absolute. So if you see it's 70,000, it's relative to polystyrene or PMMA standard. It's not really absolute. So, but anyway, we can use it for comparison. Detectors usually refractive index or UV if there are some double bonds or something that absorbs UV light. And what is good at the end, we can collect also fractions of those samples for further analysis, for example, for NMR analysis.
Just enlarge.
Then we can have another detector is SEC-MALS. Okay, some write it with 2L, some with 1L. It's also SEC with MALS detector, multi-angle light scattering detector. And this detector gives us absolute values of molecular weights. So this is it's very good because now we do not rely on standards. Also, we can use some detectors on viscosity. It's also. Then other chromatographic techniques which can be used are liquid absorption chromatography, which separates on specific, mostly attractive interaction with stationary phase. So it's not based on the molecular weight of the length of the molecule, but interactions which can be done with this stationary phase. And liquid chromatography under critical condition, this separates homopolymers according to the type of the end groups. And this is also can be very important sometimes for recycling and some for polyurethanes, for example. We can use this. It's very, very nice. Yeah. There is, of course, one more technique which is used, and this is two-dimensional liquid chromatography. So here we have two columns with different separation mechanism, which are connected in a sequence. So we have pump, we have injector, we inject, and this sample goes through the column, first column, and then it comes into this double loop well. And here this one takes some sample, turn around a little bit, it takes into the second loop, takes another one, and leave the first one to the second column, which has a different mechanism. And so we, at the end, of course, detector and everything the same. And so we see separation by HPLC separation and GPC separation. So according to molecular weight and according to the interaction with stationary phase. And of course, also here we can take fractions at the end and use NMR, for example, for further chemical characterization. So to conclude, FTIR is fast and relatively easy method for simple polymer characterization. Also can be used for quite complicated things, but it takes someone with a lot of experience to do it. More or less, this goes also for NMR, but it is, to my opinion, much easier, especially because we can use other techniques, as I said, APT or two-dimensional, which helps us. SEC is actually a standard method for molecular weight determination. Some time ago, when I started my career, viscosity was measured, but now more or less hardly someone do it. When we work with copolymers, yeah. When we work with copolymer, when we work with copolymers, other techniques and two-dimensional might also be used for full characterization. However, here the development of method of characterization sometimes is quite challenging, and it takes a lot of time. And especially good for full characterization is combination of SEC or two-dimensional chromatography with NMR. So with this, I would conclude that. Thank you for your attention.
On the size exclusion chromatography, are the peaks well defined, or there can be some overlap between them?
Oh, very often it's overlap. Yeah.
So very often.
Yeah, very often.
And it is a problem when you want to separate these different.
Sometimes you just have to use maybe different column. This can sometimes help, or at the end you take fractions and characterize fractions.
Okay.
Is there any other question from the audience online? We hear some talking. Well, if not, thank you again. And we will come to the second presentation, which was supposed to be done by Sylvester Bolka, but however, he's not available today. He's on a business trip. So Rebecca will give this presentation called Mechanical and Dynamic Mechanical Characterization of Polymers.
Okay. First, a little bit about me. My name is Rebecca Orber, and I'm assistant at TPO in polymer processing topic and functional polymers. I also do my PhD at Montana University Leuven in topic of processing of polymer-based vitrimers. And today I'm going to present mechanical and dynamical mechanical analysis and characterization of polymers. First, we'll go through some introduction, define some main properties, then we'll take a look into mechanical characterization, where we will go through tensile testing, compression testing, flexor testing, and impact testing. And then we'll go to dynamic mechanical characterization and go through some general rules of polymers related to their mechanical properties in the conclusion. So, as probably we already know, mechanical characterization is actually fundamental in polymer and all, not only limited to polymer material science. The most common approach is to test the materials via controlled stress application until sample failure. Polymer materials actually in applications must be either strong, stiff, tough, ductile, or hard. or just the right combination of all of the properties above. With the next slide, we will define all of these mechanical properties, and then we will go to the department where we go through how we measure those properties. Okay, so first, how do we define strength? Strength is actually the highest load applied before failure and is mathematically given as the force above the cross-section area. We know more than one kind of strength, and it's dependent on the type of the load we apply. So tensile, then compression, in the opposite direction, flexural if we are bending our samples, then shear or torsional. Further on, about the stiffness, actually stiffness is the ability of the material to distribute the load and resist the deformation or deflection up to center failure. It's actually expressed by moduli, either tensile, flexural, shearing, etc., in dependence of the load that we are applying to our sample. Here we have some graphs showing actually moduli the stiffness independence of density of classic materials. We can see polymers are quite of a low density and have quite nice modulus, quite high modulus. Of course, metals outperform them, but have much higher density. So the polymers are very good for example, for lightweight applications. We have on bottom on the left foams with very low density, low modulus, and elastomers with somewhere density somewhere in the range of classic polymers, but with much lower stiffness. On the other hand, if we compare the costs to the stiffness of the materials, we have polymers again somewhere in the golden middle, above with higher moduli we have composites, metals, and on the bottom foams and elastomers. Further on, if we continue, we have to find the toughness as well. Toughness is actually the ability of polymer to exhibit plastic deformation and resistance to an impact load without failure. It's actually determined as the energy absorbed by the material up to fracture per unit volume, and it's also area below the stress strain curves. Here we have some typical stress strain curves for different classes of the materials. We have first material with small toughness. Materials with small toughness are related to brittle fractures like ceramics. Then we have material with large toughnesses, large surface area below the stress strain curve. For example, like metals. And then we have materials with small toughness, which are unreinforced polymers, and ductile fractures are characteristic for such materials. Then we also have to define hardness. Hardness is a property that we notice it gets really many times confused with strength or stiffness, but it's actually defined as the resistance of material to local plastic deformations. So resistance of material resists the indentation of other material. Most well known is Mohs hardness test, and it's actually done via scratching of one material with other material with known hardness on the Mohs hardness scale. For the polymer materials, shore A and shore B are most common for the softer materials, and Brinell and Rockwell hardness test are also very well known. For Brinell hardness test, it's characteristic that the ball is indentated in the samples. It's very often used with metals and castings. And Rockwell hardness test is actually can be done for all type of materials. It has a different scale, ABC, up to, I think, the whole alphabet is actually defined as scales. And according to our sample hardness, we have to choose the right scale, and the tools to measure on that scale are given in ISO 2139 standard. So how do we measure those properties? First, in ensuring reliable outcome data, standard methods are vital. Standard methods are actually true in most all fields, can be either ASTM, ISO, DIN, etc. Today we will focus on ISO recommendations. And if we claim some property to be true, it must be backed by a method, which is usually given in standards, and statistical analysis. We need to have more measurements for each samples so that we have mean values and standard deviations. Actually, how many samples we have to measure for one value is also given in standards for the method we are using. And actually, in material science, for material development, we also have to have material development supported by proper results, meaning proper standardized methods and statistical analysis. If we move forward to mechanical characterization, first we will go through the tensile testing. Tensile test is actually most widely spread mechanical test. For the determination of tensile properties of polymers, we use ISO 527. Tensile test can be actually otherwise modified and employed for testing of adhesion, bond strength, peel forces, tear resistance, crimp joint pull force. Actually, based where we can apply the tensile force. Here we have the machine for tensile test that we will use later on today. We have grips and sample between the grips and the low cell which measures the force that we apply to the sample. Sample sizes and shapes are also given in the standard. With ISO 527, we have two recommended shapes. It's either 1BA or 5A and 5B. Those are 1 and 5 give us the shape, and BA, the letters, or AB give us the size. We will use today on the practical workshop the samples of type 1BA. For each sample, standard provides us with upper and minimal dimensions, which we need to know to set properly the methods so that we use the strain, the speeds and stuff that will give us the most relevant results. Type B, type 5 specimens are usually more employed for softer materials, which are more rubber-like or elastomers. With the polymers we will see four typical shapes of stress strain curves. First is a curve of a brittle material, like we've seen previously with ceramic-like materials. It's in polymers, it's known composites and amorphous polymers. So the materials that are not really tough and break at low strains, but have higher tensile strengths. Curve B represent semi-rigid material with strain hardening after yielding. Example of such materials are polyethylene, polypropylene, and then C, we have the curve that gives us no strain hardening after the yielding. It's known for materials such as ABS. And then we have D-shaped curve, which is known for flexible materials, soft rubber-like materials. And the quantities that we are interested in with tensile testing are tensile strength. Tensile strength is given as first maxima on the curves, or in case of D-shaped curve, where we don't have maxima, they're usually given as tensile strength at certain strain. It's strain is usually 100% sand or 300% in rubbers. The quantities of interest are also strain at tensile strength, so the strain at first maxima and strains at break. Okay. So the second most important thing here is modulus of elasticity, or Young's modulus. Is actually, as we already mentioned, the measure of stiffness or resistance to elastic deformation under stress. Mathematically is given as a strain above the difference in stress above the difference in strain. We actually measure modulus of elasticity in the elastic region. So this is for polymers defined by the standard up to 0.5 of elongation. This is also the region where Hooke's law is applicable, which tells us that stress is actually modulus times strain. Again, we have some different stress strain curves for different materials. With materials, number one, we have high modulus, high stiffness. Material two is somewhere in between. And material three, very flexible, rubber-like, low moduli material. With tensile test, we also can measure Poisson's ratio. It's very important quantity, especially in structure applications and for foams. For polymers, it's between 0.2 and 0.4. Usual value is around 0.3. And it's actually a ratio between the lateral strain above the longitudinal strain. So if we move further to compression testing, we will go really briefly through the compression testing because it's basically the same principle and same logics apply as for tensile testing, with the only exception that the logic is actually applied in the opposite direction. Compression testing is defined by ISO 604 standard for compressive properties of plastics. It's used for rigid, semi-rigid plastics, elastomers, and especially foams. If we continue with flexural testing, actually flexural testing is golden standard test for composites, because composites have high stiffness, high strength, and with tensile tests we can have gripping problems. They can slip or they can break in the grips. With flexural tests, we have different measuring principles. We can have samples fixed on one side and apply force on the free side. 3 and 4 point bending approaches are the most common, and today we will see the 3 point bending approach later in the afternoon. And determination of flexural properties is standardized by ISO 178. In ISO 178, we can have specimen sizes, recommendations, and actually measuring setup recommendations. We will use a sample with thickness of 4 millimeters times 10 millimeters and length of 18 millimeters. The sample cross sections are very important so that we can set proper speeds for the testing. Also with flexural tests, we have some characteristics. There are 3 with comparison of 4 with the tensor, because we cannot measure really flexible samples. We have a curve which represents specimen that breaks actually before yielding. We have then B curve. It's for specimens that gives us a maximum and then break before the conventional deflection. And type C curve, where we have specimens that neither give us a maxima nor break before the conventional deflection. Again, flexural strength is given by first maxima, or in case that we don't get a maxima, it's we take the value at strain that's 1.5 times thickness of the sample. Again, other quantities of interest are strains at flexural strengths and strains at break. With flexural modulus, it's very similar as the tensile modulus. We determine it as in the elastic region up to 0.25 of strain. If we continue with the impact testing, with impact testing, we actually study material behavior under impact loads. We measure energy absorbed by the sample during the load applied in the impact wave. It's a destructive method as or the rest of all. We study actually impact toughness of materials and notch sensitivity of the materials. We can have test unmatched samples or notch samples. The notched impact toughness and ordinary impact toughness are not always following the same trends, because notch is actually used to concentrate the stress at the end of the notch, and not all materials actually are sensitive. Some materials are more and some are less sensitive to the stress concentration. The tests are actually applicable to all material classes, and the most common approaches are ISO and Sharpie, standardized by ISO 180 and 179. And actually, the measurement principle samples are the same, with the only exception that we have some differences in mounting of the sample. With Sharpie tests, we mount the sample on both sides, and with ISO test, the sample is mounted on one side and it's free on the other. Okay. So we have here presented the testing setup. The testing setup consists of pendulum, which gives us known amount of energy, sample support. When we drop the pendulum, the potential energy converts to kinetic and back to potential, and impact toughness is actually then calculated with from the difference between the pendulum drop without the sample and with the sample. So the difference in the angle. Here we have some recommended sample sizes by IC 179 -1 standard. We also have standardized notch sizes, and they're actually the same for ISOT tests. A little bit about the property dependence of the toughness. Here we have results of ISOT impact strength test for polyethylene of high density, polypropylene, and polystyrene. HDP and PP are actually of crystalline polymers. Polystyrene is amorphous, and they are filled with different volumetric fraction of iron particles. You see that crystalline polymers have higher impact strengths. With amorphous, we get a really low impact strength because they're quite brittle. And as we add higher volumetric proportions of fillers, we get also lower impact strength. Because the filler is brittle by itself, and it usually is working as impurity in the matrix. Okay, so if we move further to dynamical mechanical characterization, DMI is actually widely used to characterize materials' properties as a function of temperature, time, frequency, stress, atmosphere, or combination of all the parameters above. So we usually apply small deformations to the sample in a cyclic or dynamic manner, usually in a sinusoidal way, and we measure response of the sample to stress, temperature, and frequency. Here we have actually scheme of standard 3-point bending in DMA. Here we have two supports on the side, and the sample is also clamped on the middle, and the middle clamp is connected to the fourth motor. First motor generates a wave in a sinusoidal manner, and then we have sensor here which reports the displacement. And here's also some temperature sensor. So how much our samples deform is directly related to the material stiffness. And we also get information on the damping. Damping actually dissipation of the energy. It's expressed by loss modulus or the tangent of the phase angle. So if we here we have actually storage modulus curve. with the temperature. We can see with storage modulus all the more or less all the thermal transition of first and second order. If we start low, here we have gaseous state. If we increase the temperature on molecular level, we come to local motions, and further on, after climate transition, we on the molecular level start seeing some bending, stretching. Further on, moving up to over some beta transition, we come up to mobility of the side groups. Then we have TG. If we have amorphous polymer, we would not see TG in purely crystalline polymers, but this is like theoretical stuff. When we come over the TG on the temperature scale, we actually on the molecular level start seeing some gradual main chain moves, and we notice extensive drop in storage modulus. Then we come to rubbery plateau, where we can see on molecular level some large scale chain movements. And if we increase temperature further, we come to the melting temperature, where the chains start to slip by each other. Besides the temperature transitions, we can also study coring processes via DMA. But the coring would actually be seen as the increase in storage modulus. Okay, so to get some good data out of DMA measurements, we need properly prepared specimen, right specimen geometry for the type of measurement we want to do, since we can measure on tension via single cantilever, via dual cantilever, three-point bending mode, or shearing mode, or compression on DMA, depending on the clamps that we use. It's also always important to have properly calibrated instrument and apply reasonable strains and heating rates to our samples. The reasonable strains we kind of noticed with our measurements that we wanted to apply to high strains, and the machine wasn't able to generate enough force. And with heating rates, we usually need to use heating rates low enough so the samples heat up gradually, and that they do not have too high temperature gradient inside. And then again, even in parallel specimen and even thickness of specimen, so that we have even distribution of properties and heat in the sample. About glass transition temperature detection, here we have some moduli curves against the temperature. Blue curve represents storage modulus. With the green curve is actually loss modulus, and black curve is tangents delta curve, which is actually loss modulus above storage modulus mathematically. If we want to see the TG, it's actually usually large drop, seen as a large drop in storage modulus curve of a decade and more if you use modulus logarithmic scale for the storage modulus and linear scale for the temperature. With glass transition, we also see concurrent peak in the tangents delta, and actually the reported values for glass transition temperature actually varies on the industry. We can characterize it as onset on the storage moduli curve. it can be also characterized as onset on tangents delta curve or peak of tangents delta curve or peak of osmolarity curve. So moving forward to conclusion. In the conclusions, I wanted to sum up some general rules that are determining mechanical properties of polymers. With more rigid unit networks, higher degrees of crystallinity, higher molecular weights, higher degrees of crossing in crossing polymers. We usually see higher strengths and moduli. With higher strengths and stiffness, we also usually notice the compensation on the toughness side of the polymers. If we then introduce fillers, we usually raise the stiffness. If we introduce fibers, we are able to increase strength and stiffness of the materials. But it's very important to keep the interactions between the polymers, polymer matrix, and the fibers or fillers that we are introducing on a very good level. We can help the interaction with use of compatibilizers, which actually act as the connection between the polar and non-polar components, similar to or washing detergents that are connecting oils to water. And on the other hand, if we want to improve the toughness can be improved with addition of plasticizer. And I wanted to conclude with the thought that characterization is actually basis for all the pillars that we need for proper application and use of polymer materials. So, questions?
So, thank you, Rebecca. If there is no question, now we are having a coffee break till 11 o'clock.